Okay, so we are going to proceed with the second lecture of the course, which is the continuation of the first chapter. Okay, I'm continuing. The first chapter we saw a sort of general framework in which we are going to insert the derivation of constitutive models, constitutive equations. And now in this lecture we're going to review a number of examples of using this framework to derive some constitutive models that can be useful for you either in this course or in the future. So for instance, let's consider a family of very common constitutive models, which are those models that are called based on a strain decomposition. Typically this is proper of what is called elastoplastic material. Okay? And by the way, this is one of the families of constitutive models that we are going to review in depth in this course, elastoplastic materials. Okay? What characterizes this family, this approach to this kind of constitutive models? Well, there are materials characterized what is called the inelastic strain. Materials in which the stress versus strain constitutive equation is not linear anymore, so we are not talking in general of elastic materials. It's non-linear, so it's not proportional. Double strain doesn't mean double stress up beyond a certain point. This is called elastic branch, that is called the non-proportional or inelastic branch. But most interesting is that at a certain point, upon what is called unloading, imagine that I increase the strains up to that point, and at this point, by some reason, I decide to decrease the strains, okay, release the strains, okay? And then, unlike what would happen in an elastic material, in which the behavior would be reversible and the stress-strain path in loading and in unloading is the same, in this type of materials, in this family of materials, what happens is that the unloading branch in the stress-strain space is different from the loading one. So up to that point, if I had unloaded, I would have gone this way, but just because I unload, instead of going this way, I go this way. And what is specific of this kind of materials is that if I continue releasing the stresses, decreasing the stresses up to zero, when I arrive to zero stresses, I found a non-zero strain. Okay? That's typical of, for instance, metals or many of the materials. For instance, if I take this paper, if I just subject this paper to very small loads, I see that as I release the force, the paper recovers the initial shape. So it moves along one way like that, with no strains for no stresses, okay? But if I go a little beyond, and I just produce larger strains like this one, at this point, what would I expect if I just release the forces I am applying on the piece of paper? Recover the initial shape? Not, you see? I've recovered partially, a little bit, but not totally, okay? So it means that there is a strain, but now with no stresses, then there are some irrecoverable strains, irrecoverable under unloading. So there is a wide family of materials that behave like that. Behave like that beyond a certain threshold. Beyond a certain threshold, below this threshold, they behave elastically, but beyond this threshold, they behave inelastically, and they generate what is called permanent, irrecoverable, or, in that case, plastic strains. So at every point of that, we have that the strain at this point could be split into two parts. One, which is the strain that would remain at the end of the unloading process until stress release, okay? And the remaining of the strain, strains all these, the remaining of the strain is called elastic stress, because that part of the stress is recoverable upon unloading, but this part of the stress is not, okay? So how do we model, in the context I've seen before, I've explained in lecture one, these kind of materials? Well, that's what we're going to see. There is a framework which in turn can be inserted into the general framework we talked about. First, we split the strain at every stage of the loading process into two parts. One is the inelastic strain, and the other is the elastic strain. The elastic strain is somehow related to the stress, as an elastic material does. Okay? So, if this elastic strain and the corresponding stress is essentially, if the slope of this branch is essentially the same of that, is essentially typically proportional that in elastic strain with respect to stress as an elastic material is. Okay? Well, this is what the elastic strain, and then the remaining one is what we call inelastic strain. That's first. Well, let's consider for simplification the case of isothermal case, so that we have no thermal action. We could also extend that to thermal actions, but for simplification, let's do that. And then, let's insert this model into the framework that we had visited. First, we consider the set of free variables, and by the time being, let's consider that the free variables are the strains. So that's a problem which is strain-driven, okay? This is something, so in other words, is what we know, is our entry, and then we want to obtain what? From the strains, we want to obtain what? The stresses, that's our purpose, okay? So, okay, this is defined. Then let's consider internal variables. Okay, then what is specific in these models is that the inelastic strains are considered internal variables. This internal variable, for instance, in plasticity, this plastic strain, in plasticity, this inelastic strain, is related to the micros, what happens at low levels, of lower scales of the material. Typically in crystal lattices to the dislocation of the crystals, okay? And that translates at the macroscopic levels and something which is, as I told you, internal variables. Internal variables are the way in which we incorporate at the phenomenological level, at the observable scale, phenomena that are occurring at the lower scale, okay? So this is an internal variable. And several internal variables. So this is for just 1D case, but we can consider also 2D or 3D cases in which the components of the strains are more than one. Okay? And in addition, we can also consider some additional internal variables. Let's call that alpha, which allow modeling some additional phenomenon, like for instance, what is called the way in which the material loses or keeps a strength as the plasticity takes place, which is typically the slope of this curve and so on. So we will go in the second part of this course much in depth with that concept. Of course, as we have the internal variables, immediately we have to look for something else, which is the evolution equations. And evolution equations, in the most general framework, said that the evolution of these internal variables, alpha dot and epsilon dot I, have to be a function of the free variables and the internal variables themselves. However, I have to anticipate that as a specific feature of this subfamily of constitutive models, the evolution equations are not function of the instantaneous values of the inelastic strain. Okay? This is a specific case, so it doesn't break the general rule. In the general rule, the three arguments should be here, but in these cases, we don't need to place the argument, the inelastic strains, as an argument for the evolution equations. Okay? Well, this is the framework, and then the remaining variables are dependent. That means that all them depend on the free and internal variables. So, for instance, the stresses will depend on the strain, the inelastic strain, and the internal variable alpha, and also the free energy will depend on the strain, the inelastic strain, and the alpha. So whenever I want to get the time evolution of the stresses, I have to differentiate with respect to the first argument and multiply by epsilon dot, then differentiate with respect to the second argument and multiply by epsilon dot I, and differentiate with respect to the third argument and multiply by alpha as the third dot. The same whenever I need the time evolution of the free energy. Differentiate the free energy with respect to epsilon times epsilon dot, the free respect to epsilon I times epsilon dot I, epsilon alpha respect to alpha. That's just a single calculus. Okay, so next step is, as we said, formulate the free variables, the internal variables, the evolution equations, and next step is propose a free energy function. And the free energy function in this model is also postulated based on some physical reasons that maybe you will see in more detail when we go to this family of models, that has two parts. One that just matches the free energy that we have for elastic materials, but in terms not of the total strain, but also on the elastic part of the strain. So let's see, well, in the same way that the materials have a behavior which is a sort of, in a strain, superposition of an elastic and inelastic behavior, so the free energy has an elastic energy which has the same form that we have for elastic materials in terms of the elastic strains. By the way, since elastic strains, by definition, is the difference of the total minus the inelastic strain, so finally, implicitly, that function is a function of epsilon and epsilon I. Okay? And there is a second part which is completely uncoupled. So the second part of the free energy depends only on this additional internal variable that from now on we'll call the strain-like internal variable alpha. And that's called a hardening potential because this is responsible for the hardening of the material. We'll see what does that mean. Okay, now that we have done all the ingredients, now the process of obtaining a constitutive model should be reduced to just operating, okay? And for this, we compute dissipation. I recall that dissipation could be written like that. In absence of temperature changes, that term drops, and that involves the time variation of the stresses of the free energy and sigma times epsilon dot, and that dissipation had to be positive for any possible evolution of the problem. What is the evolution related to? To epsilon dot. Epsilon dot is a free variable, so that one could take any variable, any value. Okay, so let's do it. Replace here, now if we replace, we have a term which is sigma times epsilon dot. You find it here. Epsilon dot is a common factor. And then phi dot would have a term that we had here, which is derivative of phi with respect to epsilon times epsilon dot, which is the one that appears here, grouped because they both multiply to epsilon dot. And then the term here, the derivative of phi with respect to epsilon I times epsilon dot, that appears in phi dot. The terms brings that term. And finally, that term, the derivative of phi with respect to, with respect to alpha times alpha dot, that involves the term here. Okay, so the point is that, by the way, there is some operation here. You don't hear, it should appear derivative of phi with respect to epsilon I, and it appears derivative of phi with respect to epsilon. Okay, according to that, there should appear derivative of phi with respect to epsilon I. And it appears here derivative of phi with respect to epsilon y. Well, is that if I want to differentiate that with respect to epsilon I just differentiate with respect to epsilon, is what you have here. Is derivative of rho phi with respect to epsilon, is derivative of rho phi with respect to epsilon e, derivative of rho phi with respect to epsilon e is c times epsilon, is something plus derivative of epsilon e with respect to epsilon, which is 1. Because epsilon e depends on epsilon just in a 1 times 1 in a completely equivalent manner. So that is 1. So derivative of rho phi with respect to epsilon I is equal to derivative of rho phi with respect to epsilon e is equal to derivative of rho phi with respect to epsilon. Okay, that's why it appears here. Just little mathematical arguments that you can discover on your own. And also here, that term is okay. Okay, so after that, we find that the expression of dissipation looks like that. By the way, here we have epsilon dot I. But in virtue of the evolution equations, epsilon dot I depends on the instantaneous values of epsilon and alpha. Okay? I want to emphasize that, and let's emphasize that here. And alpha dot depends on the instantaneous values of epsilon alpha through the evolution equations. Okay? Okay? So finally, looking at the functional dependence, that function, that part here, there is a function that depends on epsilon, epsilon I, and alpha that multiplies epsilon dot. And all these are functions of epsilon, epsilon I, and alpha. This is function epsilon and alpha. This is a function epsilon alpha. So all these terms here do not depend on any rate. They depend through the evolution equations only on instantaneous values of the free variables and the internal variables and alpha. I just want to point out this. You understand that? Do you follow me? Okay. So look the structure of this equation. It says that a certain function of epsilon, epsilon I alpha times epsilon dot plus all this, with a certain function of epsilon, epsilon I alpha, is greater than 0 for all epsilon dot. What are the implications of that? In order to see the implications of that, we better go to a theorem that stands for this kind of statements. Okay? Let's look at in a simplified version. Again, a Coleman's theorem. Now, we saw Coleman's theorem, and we had something times x dot plus something times y dot is equal to 0 for all x dot and y dot, and that implied, I recall, that that and that would be 0. Okay, that's what we saw in the past day. Now we are looking at a different shape of this function. Function d is a function of the instantaneous values xy times x dot, the variation of x, plus a function of xy that doesn't multiply to anything else. Okay, and this has to be greater than 0 for all possible x dot. What are the implications of that? Well, the implications are the following. That part here, multiply x dot, has to be necessarily 0. Has to be necessarily 0. And in consequence, this drops, and then only this part here remains, and then that means that this function itself, only this function, has to be always greater than 0. Proof, well, it's very easy. Imagine that this function is smaller than 0. Okay? Whatever is the value of that, since x dot is any value, I can just always find a value of x dot, which can be infinity, I mean 10,000 or 10 millions, because there is no limitation on that, that multiplies times that, just overcomes the value of that in sign. So if that is positive, if that is negative, I just take x dot positive, and then that I can make that this not fulfilled, that this term negative prevails on that. Okay, that's what is said here. On the other hand, let's imagine that f is greater than 0. Then I can always take an x dot negative, but large negative enough, in order that overcome that value and make the sum of these two terms smaller than 0. This contravening the original statement. So whenever if f of xy is greater than 0 or f of xy is smaller than 0, I can, since this is an important part of the theorem, for any x dot, I can always find some value that makes this statement false. In consequence, the only position for f of xy is not being neither positive nor negative, but being 0. And if it's 0, then this term always drops, and then g of xy is greater than 0. As simple as this. Follow? That's a very simple reasoning that you can also look at it in a little more detail, but that's the method. So whenever you have a function of instantaneous values that multiply one rate that can take any value in positive or in negative, plus another function not multiplying anything, greater than 0, which that implies then this part is 0 and that part then has to be greater than 0. Okay? So look now at the equation of the dissipation we have found. It's exactly that one. Now x stand for epsilon, okay, and y stand for epsilon I alpha. Okay? So that is just a specification or a generalization of that theorem for the cases in which have, instead of scalar variables, we have tensor or vectors or whatever. This stands doing the reasoning component by component. So finally, we found that there is, what is the conclusion of that? Applying the above theorem. What is the conclusion? That should be 0. because this is for every epsilon dot. And this part then has to be always greater than 0. Okay? So now let's apply that. Where is F and what is G? So F in that equation, look, is that part here. Is sigma minus derivative of rho phi with respect to epsilon. And this has to be 0. So as a consequence, the application of the Coleman's method to this expression of dissipation that has to be greater than 0 for any possible evolution of the problem epsilon naught makes that this is 0, and in consequence that sigma minus this is 0. So again, something that also was happening in the previous model that we visited the last day, the stresses are always the derivative of the density of free energy with respect to the strains. That's a constant. Always, look, so far, in all cases, the stresses are obtained as the derivative with respect to strains of the free energy. Okay? Then what about dissipation? Well, if that term is 0, if that term is 0, because that is this term, that means that the other terms, this term has to be 0. No, has to be 0. That term is the dissipation. That term drops. And the dissipation then can be written as the other terms, the derivative of rho phi with respect to epsilon dot I, plus the derivative of the free energy with respect to alpha dot. Okay? But look, again, the derivative of that with respect to epsilon, we have just proved that it's sigma. So that term is sigma times epsilon dot I, plus this term times alpha dot. Okay? So we obtain a general expression for the dissipation in this family of models based on the composition of the strains into an elastic and inelastic part. The dissipation is the stress times the inelastic strain plus some additional term that multiplies the evolution of the internal variables alpha dot. Okay, so that is the model, the equation of the dissipation. Then, if we have taken, let's go back to the expression that we took for the free energy, density of free energy, is 1/2 of epsilon E, which is epsilon minus epsilon I. C is the elastic operator that in isotropic materials is a typical one depending on two parameters, lambda mu, the Lamy parameters, or E nu, the Young modulus and the Poisson ratio, whatever we want to consider. And then plus the term that depends, that additional term, that's something that we saw at the beginning. We postulated that form of the free energy, okay? So what is the derivative of the free energy with respect to alpha? It doesn't depend on alpha in that term. It depends on alpha only in that term, okay? So the second term that appears here, the derivative of rho phi with respect to alpha, is nothing else than h prime of alpha, okay? The derivative of this additional part of the free energy that depends only, that's a scalar function that depends, is what called as the hardening energy, or the there is a name for that you will see, and then that derivative is normally taken as minus, and that result of this derivative, which depends on alpha, is called the hardening variable. Okay, that's part of the type of nomenclature that we use. So finally, by summarizing, the constitutive equation is, as always, that the stresses are the derivative of the free energy with respect to strain. And in that case, look, the derivative of free energy with respect to strain, how is the free energy? That, if I take the derivation of this with respect to strain, this term and 1/2 cancels, and remains C times epsilon elastic. So, look, what characterizes the stresses is that they are equal to the elastic constitutive tensor, the same that we would use for an elastic material, but now multiplying not the full strain, but the elastic part of the strain. So that's very easy to remember. So in any inelastic-based material based on inelastic decomposition of the additive decomposition of the strains, the stresses and the elastic strains are related as an elastic model. Okay? Look, the elastic strains. So that means the strains, these elastic strains in turn can be splitted or can be written as the difference of the total minus the inelastic strains. I just recall the original assumption that elastic strains are the total minus the inelastic strains. Okay? So the constitutive model is as simple as this. Conceptually, the stresses are related to the elastic part of the strains as an elastic model does. Okay? And the dissipation, well, the dissipation now is written in that way. That is good to remember. The dissipation are the product of the stresses times the inelastic strains. So, so to speak, if we think of it as the work of the stresses, sigma times epsilon dot, what is sigma times epsilon dot? Is the stress power per unit of volume. Is the work of the stresses, okay? But the work of the stresses under the inelastic strains, that is dissipative. That doesn't produce stored energy. It's just something that is lost. Any part of the work produced by the stresses times the elastic strains is part of the dissipation. And then there is another term which comes from this second term here, which is Q, the hardening variable, which, by the way, is the derivative of the hardening potential with respect to alpha, times alpha dot. And that's the expression. And that has to be greater than 0.